Hello and welcome to my students. Today's lectures we are going to discuss the new points chemical thermodynamics. In these chapters we have see the variation of chemical potential with pressure and temperature. Firstly, we are going to variation with pressure. The chemical potential for the mu I is defined as like mu I is equal to in bracket del Z up by del N1 with respect to constant temperature pressure Nz, which is equal to the free energy Gi bar, equation 1. Differentiating those above equation with respect to pressure at a constant temperature, then rewrite this equation we get like del mu I upon del P at a constant temperature Nz is equal to del square Z by del P del Ni at a constant temperature Nz, equation 2nd. But we know that the volume P is equal to del Z by del P at constant temperature. Those equation we can differentiate with respect to Ni at a constant temperature pressure and Nz. Those equation then we can rewrite like the del V by del Ni at a constant temperature pressure Nz is equal to del square Z by del P del Ni at a constant temperature Nz, equation 3rd. By definition, we know that the del V by del Ni at a constant temperature pressure and Nz is equal to Vi bar as the partial molar volume, and therefore this partial molar volume Vi bar is equal to these terms, the backside this back equation like this, del V by del Ni is equal to these terms. So del V by del Ni at a constant temperature pressure and Nj, which replaced by the partial molar volume like the Vi bar. Therefore this partial molar volume Vi bar is equal to del square Z by del P del Ni at a constant temperature Nz, equation 4. Now compare about two equations, the equation 2 and 4, we get the del mu I by del P at a constant temperature Nz is equal to Vi bar. Vi bar is a partial molar volume, and therefore the rate of change of chemical potential of the ith constituent with pressure at a constant temperature is equal to the partial molar volume of that of the constituents. Now we are going to next terms like the variation with temperatures. Then we know that these equations, the partial molar potential like mu I is equal to del Z by del N at a constant temperature pressure Nj is equal to the Gi bar. So this Gi bar as the partial free energy. This above equation can differentiate with respect to temperature at a constant pressure. Then this equation we can rewrite like the del mu I by del P at a constant temperature Nj is equal to the del square Z by del T del Ni at a constant pressure Mj. But you know that the entropy, it is a minus S, is equal to del Z by del T at a constant pressure. Then put this value, those equation also we can differentiate with respect to the Ni at a constant temperature pressure and Nj, and therefore this equation we can rewrite like minus del S by del Ni at a constant temperature pressure Nj is equal to del square Z by del T del Ni at a constant pressure Nj, equation third. But by definition of partial molar properties like del S by del Ni at a constant temperature pressure Nj is equal to Si bar. These terms we have seen last times, like partial molar entropies. This partial molar entropy Si bar is equal to this del S by del Ni at a constant temperature pressure Nj. Put this value in above equation, we get the Si bar minus Si bar is equal to del square Z by del T del Ni at a constant pressure Nj. Then compare the equation 2 and 5, then we get then del mu I by del P at a constant temperature Nj is equal to Si bar. Now we have see the next derivations like the Gibbs Duhem equation. These Gibbs Duhem equations are mainly used to show the change in chemical potential of one components, they cause corresponding change in chemical potential of the other components. And this relation between this chemical potential of one components can be changed, which will shows by there is corresponding decrease in chemical potential of other component in such a way that the sum of the changes in the zero or the total system. So this Gibbs Duhem equation we can describe are here like dz is equal to del z by del t at constant pressure N1, N2, so on dt, plus del z by del p at a constant temperature N1, N2, dp, plus del z by del N1 with rest temperature pressure N2, so on dN1, plus del z by del N2 at a constant temperature pressure N1 dN2. This equation 1. This equation can rewrite like this: the del z by del t at a constant pressure N1, N2 dt, plus del z by del p at a dp at a constant temperature N1, N2, plus the mu1 dN1 plus mu2 dN2. This equation second. But at a constant temperature and pressure, the above equation can be reduced like dz at a constant temperature and pressure is equal to the mu1 dN1 plus mu2 dN1. Equation third. By integration above this equation, then we get G, that is a free energy, Gibbs free energy at a constant temperature and pressure is equal to mu1 N1 plus mu2 N2. Equation fourth. By differentiate this equation, we get dz at a constant temperature and pressure is equal to mu1 dN1 plus N1 d mu1 plus mu2 dN2 plus N2 d mu2. Then above equation will rearrange, we get like dz at a constant temperature pressure is equal to, in first bracket, like mu1 dN1 plus mu2 dN2 plus N1 d mu1 plus N2 d mu2. Equation 5. Then we compare this equation 5 and 3, we get, C is here, this equation 5 and 3, we compare these two equations, then what happens? Put this value are here, like mu1 dN1, mu2 dN2, then what happens? This N1 d mu1 plus N2 d mu2, they will be 0. In generals, for ith components, this equation can rewrite like N d mu1 plus N2 d mu2 plus N3 d mu3 plus so on equal to 0. Or for ith components like summation Ni d mu I equal to 0. This equation 6. These 6 number equations, which is called as the Gibbs Duhem equations. These equations of the Gibbs-Duhem is immense signifies in physical chemistry. It can be used to study the solution, liquid vapor equilibria, and derivations of phase rules. For a system of two components, we can apply for this equation like the n1 d mu1 is equal to minus n2 d mu2 or d mu1 is equal to minus n2 by n1 d mu2. This is another form of Gibbs-Duhem equation for the binary mixture, and therefore this Gibbs-Duhem equation can show the change in chemical potential of one component. They cause corresponding change in chemical potential of the other components. The negative sign indicates that if there is increase in chemical potential of one component, there is corresponding decrease in the chemical potential of the other components. Then next points we have learned are here. The concept of fugacity, activity, and activity coefficient. But you know that is partial molar volume of this equation phi I bar is equal to del mu I by del P is the equation 1. But you know that for ideal gas equation is PV is equal to nRT. Those equations rearranged, then we get like RT is equal to pressure P into V upon N, and therefore this phi I bar is equal to RT by P. Substitute this equation in 1, then we get RT upon P is equal to del mu upon del P, equation 4th. And therefore this del mu is equal to rearrange of this equation, then we get the d mu is equal to RT into dP upon P. Integrate this equation 5, we get then mu is equal to RT ln P plus C. C is the integration constant. If the pressure is equal to 1, mu is equal to C is equal to mu 0. It is a chemical potential under a standard conditions of a unit pressure. Then above equation becomes like mu is equal to mu 0 plus RT ln P. This equation was obtained by using an ideal gas equation, and hence it is not valid for the real gas. By applying those equations for real gas, the scientist Lewis can introduce the concept fugacity, like the F, and this fugacity are represent escaping tendency, and it has the same dimension as like a pressure, and this equation becomes like mu is equal to mu 0 plus RT ln F. But any real gas, they can behave, but that times they will have the pressure equal to 0 and fugacity is equal to this pressure, and the chemical potential for an ideal gas in mixture of ideal gas, the chemical potential of ith components can be given by like the mu I is equal to the mu I 0 plus RT ln Pi. This Pi is the partial pressure of ith components. The partial pressure is proportional to its mole fraction Xi. Like this partial pressure Pi is equal to the Xip, means partial pressure of ith components, they can be equal to the mole fraction of Xi component. And the concentrations, the partial pressure of ith component is equal to CIRT, and hence this equation can becomes like mu I is equal to mu 0 plus RT ln Xi. And by using the concentration terms, this equation can becomes like mu I is equal to the mu 0 capital C plus RT ln Ci. Therefore, for real and non-ideal system, the two equation can require the coefficient of the components, like this equation we can modify and express as the mu I is equal to mu 0 x plus RT ln gamma I xi. Mu I is equal to mu 0 C capital C plus RT ln this FICI, where this gamma I and this Fi are called as the activity coefficient of the component. The activity means it can measure the extent of deviation from which is represent the ideal behavior. And therefore, as the real gas can behave ideal, that times this gamma I equal to 1 and the product gamma I and Xi and Fi and Ci, which are known as the activity of the ith components and which is denoted by Ai, and hence this equation can becomes like mu I is equal to mu 0 into capital C plus RT ln Ai.